You have spent your whole life believing that you are one person, living one life, moving along one line through time. You make a choice, and the roads you did not take simply vanish, harmless, gone, as if they were never really there. But here is what our most fundamental equations quietly refuse to say. A single particle, left alone, does not choose. It does every possible thing at once. The mathematics that runs the universe never once picks a single outcome, and the only way physicists get a single world out of it is to add a step, by hand, that nobody has ever been able to define or even locate. In 1957, a young man at Princeton asked what would happen if you simply deleted that step and believed the equation. The answer was that nothing is ever lost. Every road you did not take is a road that another version of you is walking right now. Get comfortable and let your eyes close if they want to. Hit subscribe if you are new here, because by the end of this, the single solid life you think you are living is going to feel like one quiet thread in something far larger than you ever imagined. Now, let's slowly ease into this. Part 1. Only one thing happened. Think back to a small moment from earlier today. Maybe you stood in front of an open refrigerator and chose one thing to drink instead of another. Maybe you took the longer route somewhere, or the shorter one. Maybe you picked up your phone, or set it down, or said yes when you might have said no. Whatever it was, you made a choice, and then one thing happened. The drink you didn't pour stayed in the bottle. The road you didn't take stayed empty of you. The world moved forward along a single line, the way it always seems to, and you never once questioned that this is simply how reality works. One moment leads to the next. One outcome arrives, and all the others quietly disappear, as though they were never really there at all. This feeling is so basic that we almost never put it into words. We live our whole lives inside a single story, a single thread of cause and effect, and that thread feels like the only one there could possibly be. You are sitting or lying somewhere right now, listening to this, and it seems obvious that this is the only version of you doing so. There is one you, there is one room, there is one history that led here, and one future stretching ahead, and at every fork in that future, you will go one way and not the others. Only one thing will happen. Only one thing ever happens. I want you to hold on to that phrase tonight, because we are going to spend the next while slowly taking it apart. Only one thing happened. It is such a quiet, reasonable belief. It is also, according to one of the most serious and most disturbing ideas in modern physics, possibly the largest illusion any of us will ever live inside. Because there is a reading of our deepest physical laws, taken completely literally, in which that drink you didn't pour was poured after all. The road you didn't take was taken. The word you swallowed was spoken. Not in your imagination, not as a metaphor, but in a real place, by a real version of you, just as solid and certain and convinced of being the only one as you feel right now. The idea is called the many worlds interpretation of quantum mechanics, and the title of tonight's video asks the question that draws most people to it. What if every choice splits the universe? It is a beautiful, romantic image, and I want to be honest with you from the very beginning, because the truth is stranger than the romance. The universe does not sit and watch your decisions and politely divide itself each time you can't make up your mind. The splitting, if it is real, has almost nothing to do with you choosing a drink. It is happening constantly, everywhere, at a level far beneath your choices, in the behavior of particles so small that the word small barely applies to them. Your choices are not the cause of the branching. Your choices are passengers, riding along on top of something that was already dividing the world 1 trillion times over before you ever woke up this morning. That gap, between the gentle story in the title and the much wilder truth underneath it, is exactly where tonight's wonder lives. So let me ask you to get comfortable, to let your shoulders drop, and to set aside, just for the next couple of hours, the certainty that you are one person living one life. We are going to follow this idea all the way down, from a single particle in a quiet laboratory to a lonely graduate student who proposed something his heroes could not forgive, to the unsettling possibility that you are not a single thread at all, but a forking river, branching away from yourself again and again in total silence right now. And we are going to begin where all of this began, with a discovery so strange that the people who made it spent the rest of their lives arguing about what it actually meant. It is worth pausing on just how total this assumption is, because we almost never see it for what it is. From the moment you were old enough to understand anything, the world taught you that events have a single track. A ball thrown into the air comes down in one place. A glass that falls either breaks or it doesn't. A day either rains or stays dry. Every story you were ever told had one plot, and every memory you carry has one version. Your entire sense of being a self depends on this. You are the person who did these particular things, who took these particular roads, and the roads you didn't take feel like nothing at all, like empty space, like possibilities that flickered for a moment and then simply went out, harmless and gone. We treat the paths not taken as a kind of soft fiction, a daydream of what might have been. We are very sure they are not real places. And philosophers and physicists, for most of history, agreed with you. The whole machinery of classical physics, the physics of Newton, the physics that builds bridges and lands spacecraft, is built on exactly this single-track picture. You give it the state of the world right now, and it hands you back one future, definite and unique. There was never any need to ask about the other futures, because in that picture there were no other futures. There was the way things would go, and that was all. For 200 years, this worked so beautifully that it seemed less like an assumption and more like the bedrock of reality itself. The universe was a clock, and a clock does not branch. It ticks forward, 1 second at a time, along one line. Then, in the early 20th century, physics went looking at the smallest things in nature, the particles that everything else is made of, and the single-track picture began to come apart in its hands. What it found down there was not a clock. It was something that has never stopped unsettling the people who study it, something that suggests, when you read it without flinching, that the path not taken might be taken after all, in a place as solid as the chair beneath you. To see why anyone would believe something so contrary to everything you feel, we have to go down to that smallest scale and watch, very slowly and very quietly, what a single particle actually does when no one is forcing it to choose. Part 2. The thing that is in two places. To understand why anyone would seriously propose that the universe is constantly splitting, you first have to feel, in your own mind, the problem that drove them to it. And that problem starts with something almost absurdly small. Picture a single electron. It is one of the basic building blocks of every atom in your body, in this room, in the entire world you can see. For most of the history of science, people imagined a particle like this as a tiny solid ball, a little speck of matter that, at any given moment, is in one definite place, doing one definite thing. That picture feels completely natural. It is also, as far as we can tell, wrong. Here is the experiment that broke the old picture, and it is worth letting it settle in slowly, because everything tonight grows out of it. Imagine a wall with two narrow slits cut into it, side by side, and a screen behind that wall that lights up wherever a particle strikes it. Now imagine firing electrons at that wall, one at a time, with long pauses in between, so that there is never more than a single electron in flight at once. Each electron either has to go through the left slit or the right slit, and then land somewhere on the screen behind. If electrons were simply tiny balls, you would expect them to pile up in two stripes on the screen, one stripe behind each slit, the way paint would if you flicked it through two gaps. That is the sensible expectation. That is not what happens. What actually builds up on that screen, dot by dot, electron by electron, is a pattern of many stripes. Bright bands separated by dark bands, the unmistakable signature of waves overlapping and interfering with one another. It is the same pattern you would see if you dropped two stones into a still pond and watched the ripples cross, reinforcing each other in some places and cancelling out in others. But there is only one electron going through at a time. There is nothing for it to interfere with except, somehow, itself. The only way to make sense of the pattern is to accept that each single electron does not go through one slit or the other. It goes through both at once, as a spread-out wave of possibility, passing through the left slit and the right slit, simultaneously, overlapping with itself on the far side, and only becoming a single point when it finally lands and is recorded. This is the phenomenon physicists call superposition, and it sits at the very foundation of quantum mechanics. A quantum system, before it is measured, does not have to be in one state. It can be in a combination of states at the same time, a weighted mixture of possibilities, all genuinely present, all contributing to what happens next. The electron is not secretly in one slit, while we are merely ignorant of which one. If that were true, if it had really gone through just one slit and we simply didn't know which, then the interference pattern would vanish. It only appears because the electron truly travels both paths. The mathematics that describes this is something called the wave function, and it is the most successful description of reality ever written down. It tells you, with extraordinary precision, how these waves of possibility evolve and spread and overlap as time goes on. And here is the feature of the wave function that will matter most for everything that follows tonight. The equation that governs how it changes, written by Erwin Schrödinger in 1926, is smooth, continuous, and perfectly predictable. Feed it a quantum system, and it will tell you exactly how that system's wave of possibility will unfold, moment by moment, forever. There is nothing random in it. There is nothing that ever forces the electron to choose. Left entirely to the Schrödinger equation, that electron stays in its superposition, both paths at once, spreading and combining, with no point in the process where the many possibilities collapse down into a single fact. The equation, by itself, never picks a winner. It just keeps every possibility alive. That should already feel like a small crack opening in the floor beneath the idea that only one thing ever happens. Because if the deepest law we have for how matter behaves never selects a single outcome, then a question forces itself on us, and it is a question that has haunted physics for nearly 100 years. Why, when we actually look, do we only ever see one? Let me slow this down and put you right beside the experiment, because no description does it justice until you picture it happening. Imagine the room is dark and very still. In front of you is the barrier with its two thin slits, and beyond it the screen, waiting. You release a single electron. It is one particle, indivisible, the smallest unit of its kind. Common sense says it must pass through the left slit or the right slit, the way a thrown pebble must go through one gap in a fence. So you might decide to bet on the left. But the electron does not behave like a pebble. It leaves its source as a small, spread-out wave of possibility, and that wave reaches the barrier and washes over both slits at once. Two new ripples emerge on the far side, one from each slit, and they spread toward the screen and lay themselves over one another. Where two crests meet, the possibility grows stronger. Where a crest meets a trough, the possibility cancels to nothing. And only at the very last instant, when the electron is finally absorbed and recorded, does all of that spread-out possibility gather itself into a single bright point on the screen. You see one dot. You saw one electron. But the place it chose to land was decided by a wave that had quietly travelled through both openings, a wave with no respect at all for the idea that a thing must be in one place. Do it again and again, 10,000 times, one lonely electron at a time, and the dots slowly assemble themselves into those bright and dark bands, the fingerprint of a wave that went both ways. There is no other honest reading of it. Each particle, by itself, interfered with itself, which means each particle, by itself, took both paths. This is the single experimental fact from which everything tonight follows, and it has been confirmed countless times, with electrons, with whole atoms, even with molecules made of hundreds of atoms. The largeness of our everyday world hides it from us, but the smallness of the quantum world wears it openly. Down there, being in two places at once is not a paradox. It is just Tuesday. The wave function is simply the mathematical object that keeps track of all of this. For every possibility a system has, the wave function assigns a number called an amplitude that captures how much of that possibility is present and how it will combine with the others. These amplitudes can add together or cancel out, which is exactly what produces interference. And the Schrödinger equation is the rule that tells you how all those amplitudes flow and change from one moment to the next, smoothly, predictably, with every possibility carried along and none of them ever thrown away. I want that fact to settle in before we go on, because it is the quiet engine of the whole story. Left to itself, the equation does not choose. It keeps everything. The choosing, the collapse down to a single dot, a single outcome, a single world, is something we have to add by hand, and the moment you look closely at what we are adding, the floor begins to tilt. There is one more feature of the quantum world we need before we go on, because it is the thread that ties single particles to whole universes, and it is called entanglement. When two quantum systems interact, their wave functions can become woven together so completely that you can no longer describe one without the other. They share a single combined state, even after they drift apart, even if one ends up on the far side of a room or the far side of a galaxy. Measure one, and you instantly know something about the other, because they were never really two separate things in the first place. They are two ends of one quantum object. This sounds like a curiosity, a special trick that happens in careful experiments, but it is the opposite of rare. Entanglement is what happens by default whenever anything interacts with anything else, which is to say, constantly, everywhere, all the time. Every collision, every absorption of light, every brush of one particle against another, weaves the participants into a larger, shared state. And this is the quiet mechanism by which a single particle's two places at once spreads outward into the world. The particle's superposition does not stay locked in the particle. It infects whatever the particle touches, and then whatever that touches, rippling outward through the chain of interactions like a rumour passing through a crowd, until something as small as one electron's indecision has reached up and entangled itself with the dial of a detector, the air of a room, the eye of an observer. Hold that idea, because it is the bridge. When you understand that superposition spreads by entanglement, and that entanglement is constant and universal, you are most of the way to seeing how the strangeness of one particle could become the branching of an entire world. Part 3. The magic word. You can do this experiment in a slightly crueler way, and when you do, the mystery sharpens into something genuinely uncomfortable. Go back to the two slits and the single electron passing through both at once. Now place a tiny detector at the slits, a little instrument whose only job is to notice which slit each electron actually goes through. You are not blocking anything, you are just watching. And the moment you watch, the moment you force the electron to reveal a definite path, the interference pattern on the screen disappears. The many bright bands collapse into the two simple stripes you would have expected from little solid balls all along. The electron stops behaving like a spread-out wave that went both ways and starts behaving like a particle that went one way. Look, and it picks a side. Stop looking, and it goes back to being everywhere it could be. This is the famous, maddening feature of quantum mechanics that no amount of familiarity ever quite tames. The act of measurement seems to change reality. As long as a system is left alone, it evolves as a smooth superposition of all its possibilities, exactly as the Schrödinger equation says it should. But the instant a measurement is made, all of those possibilities except one vanish, and a single definite outcome snaps into existence. Physicists gave this sudden vanishing a name. They call it the collapse of the wave function. Before measurement, many possibilities. At the moment of measurement, collapse, and then only one. The trouble is that nobody has ever been able to say what a measurement actually is. And this is not a small gap. It is a hole in the middle of our best theory of reality. Think about what a measuring device really is. It is made of atoms. Those atoms are made of the same electrons and protons and neutrons as everything else, all of which obey the Schrödinger equation. The detector at the slit is not built from some special magical substance exempt from the laws of physics. It is ordinary matter. So why would ordinary matter, arranged into the shape of a detector, suddenly have the power to reach into a quantum system and force it to abandon all but one of its possibilities? Where exactly does the collapse happen? When the electron touches the detector? When the detector's needle moves? When the result is printed? When a human being finally glances at the readout and understands it? The theory does not say. It simply tells you that somewhere along that chain, the magic word measurement applies, the possibilities collapse, and one outcome survives. For a long time, the standard answer to this discomfort was essentially to stop asking. This approach is usually called the Copenhagen interpretation, after the city where Niels Bohr, one of the founding giants of quantum physics, did his work. The Copenhagen view, put simply, says that the wave function describes the quantum world. That measurement causes a real and irreducible collapse to a single outcome, that the outcome is genuinely random with probabilities given by the mathematics, and that it is not the job of physics to ask what is happening in between or what counts as a measurement in the first place. The theory predicts what you will see when you look, and it does so with perfect accuracy, and for most working physicists, for most of a century, that was deemed to be enough. Shut up and calculate, as the saying went. The equations work. Do not lose sleep over what they mean. But some people could not stop losing sleep over it, because if you take it seriously, the Copenhagen story asks you to believe in two completely different sets of rules running the same universe. Rule 1, for when nobody is looking, is the smooth, deterministic, possibility-preserving Schrödinger equation. Rule 2, for the special moment of measurement, is a sudden, random, possibility-destroying collapse that the theory cannot define, cannot locate in time, and cannot explain. It is as if the universe ran on physics most of the time, and then, whenever someone happened to check, briefly switched over to a different kind of magic, and then switched back. To a certain kind of mind, that is not an answer. That is a confession that we do not understand our own theory. Erwin Schrödinger himself, the very man whose equation sat at the center of all this, found the situation intolerable, and in 1935 he came up with a thought experiment to show just how absurd it could become. He imagined a cat sealed in a box, along with a single radioactive atom, a detector, and a flask of poison. If the atom decays, the detector triggers, the flask breaks, and the cat dies. If the atom does not decay, the cat lives. But a radioactive atom is a quantum system, and until it is measured, it exists in a superposition of decayed and not decayed, both at once. And if the atom is both decayed and not decayed, then the chain of cause and effect leading from it means the cat, too, must be in a superposition, alive and dead at the same time. not alive or dead, and we don't know which. Both, genuinely, until someone opens the box and looks, at which point the wave function collapses and the cat becomes one or the other. Schrödinger did not offer this as a wonder. He offered it as a reduction to absurdity, a way of saying, look how ridiculous your collapse becomes when you scale it up to something we can picture. And yet the absurdity would not go away. The cat sat there in its box, alive and dead, for decades, daring physics to explain it. Before we meet that student, I want to make sure you feel just how uncomfortable the standard answer really was, because comfort with it usually comes from not looking closely. Consider what the collapse asks you to accept. It asks you to believe that there are two kinds of physical process in the universe. One kind, the ordinary kind, is the smooth flow of the wave function, and it happens whenever nobody is looking, and it preserves every possibility. The other kind, the collapse, happens only during measurement, and it destroys every possibility but one, instantly, randomly, and irreversibly. And the theory never tells you which process is happening when, because it never tells you what a measurement is. A photographic plate? A Geiger counter? A cat's nervous system? A human retina? A conscious mind? Different physicists, including some of the founders, gave different answers, and some of them, in their darker moments, suggested that consciousness itself was the thing that collapsed the wave function, that the universe stayed in a haze of possibility until a mind looked at it and made it real. That is a genuinely strange thing for a science to be saying, and yet it was, for a long time, close to the official position. The phrase that came to define the working physicist's attitude to all this was blunt and a little weary. Shut up and calculate. It meant, in effect, do not ask what the theory means, just use it to predict your measurements, because it predicts them perfectly, and that is your job. And as a practical matter, it was completely reasonable. The equations never failed. Lasers worked. Transistors worked. The entire revolution of modern electronics was built on quantum mechanics by people who never once needed to know what happened to the cat. But shut up and calculate is an instruction about how to do your work. It is not an answer to the question of what is real, and a certain kind of person could not let the question go. If your most successful theory contains a process you cannot define, occurring at a time you cannot specify, producing the single reality you live in out of a haze of possibilities you can never see, then either the theory is incomplete, or it is telling you something about the world that you have not yet been brave enough to hear. The cat in the box was not just a puzzle about cats. It was a dare. And in the middle of the 1950s, a young man at Princeton decided to take the dare seriously, more seriously than almost anyone before him, by asking a question almost no one had dared to ask out loud. What if there is no second rule at all? Part 4. The Graduate Student's Heresy. The young man's name was Hugh Everett III. He was born in Washington in 1930, and by the middle of the 1950s, he was a graduate student in physics at Princeton University, one of the most demanding places in the world to study the subject. By every account, he was brilliant, restless, and a little irreverent, a chain smoker who loved a good argument and was not especially impressed by authority for its own sake. His doctoral advisor was John Archibald Wheeler, one of the most respected physicists alive, a man who had worked with Bohr himself, and who would go on to coin the term black hole. Wheeler had 1 foot in the world of the founders and 1 foot in the future, and he gave his student room to think dangerous thoughts. Everett took that room and ran with it further than anyone expected. The thought that consumed Everett was the same contradiction we have been circling. 2 rules, one for ordinary time and one for measurement, sitting awkwardly together in the same theory, with no clear boundary between them and no explanation for how one gives way to the other. Most physicists treated this as a philosophical nuisance to be managed, and then ignored. Everett treated it as a flaw to be fixed. And the fix he proposed was so simple and so radical that it took the field years to even understand what he was really saying. He asked the question that almost no one asks when faced with two rules that don't fit together. He asked whether we might only need one of them. His proposal was this: throw away the collapse. Throw away the second rule entirely. Keep only the Schrödinger equation, the smooth and deterministic one, and insist that it applies to absolutely everything, with no exceptions, ever. Not just to electrons and atoms, but to detectors, to laboratories, to cats, to physicists, to the entire universe taken as a single quantum system described by a single wave function. There is no special moment of measurement where the rules change, because there are no special objects called measuring devices, and no special beings called observers. There is just the wave function of everything, evolving forever according to one unbroken law. At first, this sounds like it should make the problem worse, not better. After all, the whole reason collapse was invented was to explain why we only ever see one outcome. If you refuse to let the wave function collapse, then the electron stays in its superposition, the radioactive atom stays both decayed and not decayed, and the cat, by the logic Schrödinger laid out, stays both alive and dead. So how could getting rid of collapse possibly help? How could a theory in which nothing ever resolves into a single outcome describe a world in which we always, without fail, experience exactly one? Everett's answer is the turn that changes everything, and it is worth slowing right down to take it in. He said, yes, the cat is both alive and dead, and yes, the atom is both decayed and not decayed, and yes, every possibility really does persist. But then he asked what happens when you, the observer, become part of the system. When you open the box and look at the cat, you are made of atoms too, and you obey the Schrödinger equation too. So the equation does not collapse the cat into one state. Instead, it does something far stranger. It entangles you with the cat. The version of the cat that is alive becomes correlated with a version of you that sees a living cat. The version of the cat that is dead becomes correlated with a version of you that sees a dead cat. Both of these combinations are now part of the wave function. Both are completely real. The equation has not selected one. It has produced both, and it has produced a copy of you to go with each. This is what people mean when they talk about the universe splitting, although Everett himself preferred gentler language. He called his idea the relative state formulation, because each outcome of the cat is real relative to the corresponding version of the observer who saw it. There is a you for whom the cat lived, and that is the only cat that you remembers. There is a you for whom the cat died, and that is the only cat that you remembers. Neither of you feels split. Neither of you feels like a copy. Each simply finds a single definite cat and a single definite world, and each is completely convinced that the wave function collapsed and only one thing happened, when in truth nothing collapsed at all. The appearance of collapse, the apparent vanishing of every possibility but one, is what branching feels like from the inside. You do not experience all the outcomes, because there is no single you left to experience them. There is one of you per outcome, and each one experiences exactly one world. Sit with that for a moment, because it really is one of the most audacious ideas anyone has ever had. Everett did not add anything to quantum mechanics to get this result. He took something away. He removed the mysterious collapse, the part nobody could define, and what remained, the bare equation applied honestly to everything, already contained the many worlds. They were not an extra assumption. They were what the mathematics had been quietly saying all along, if only someone were willing to read it without flinching. It helps to understand why this idea could only have come from someone like Everett, and why it almost had to come from a young person rather than an established one. The founders of quantum mechanics had spent their careers learning to live with the collapse, building their intuitions around it, treating it as one of the fixed features of the world. To them, questioning collapse was like questioning gravity. But Everett came at the theory fresh, with a mathematician's eye and very little reverence. And where his elders saw a settled framework, he saw an inconsistency that any honest reader should be able to spot. He was also, by temperament, drawn to game theory and logic and the cold clarity of optimization problems, the kind of thinking that asks not what feels right, but what the rules, followed strictly, actually require. Applied to quantum mechanics, that habit of mind led him somewhere his teachers could not follow. He simply took the equation at its word and refused to add anything it did not contain. There is a detail worth holding on to here, because it captures the whole spirit of the idea. Everett did not set out to prove that there are many worlds. He set out to find the simplest possible version of quantum mechanics, the version with the fewest moving parts. And the many worlds were what fell out of that search, unbidden, almost unwanted. When you strip the theory down to nothing but the wave function and the Schrödinger equation, and you ask what that bare theory describes, it describes a universe in which observers split. The worlds were not the goal. They were the residue left behind once the unnecessary parts were removed. This is why defenders of the idea bristle at being called extravagant. From the inside, it does not feel like adding worlds. It feels like refusing to add a collapse and then being honest about what is left. To make the relative state idea concrete, picture the simplest possible measurement once more, but watch the bookkeeping. Before the measurement, the electron is in a combination of two states, and the observer is in a single state, ready and waiting. The Schrödinger equation, being linear, treats each part of the electron's combination separately and then adds the results. So the part where the electron is spin-up evolves into a world where the electron is spin-up and the observer has recorded up. The part where the electron is spin-down evolves into a world where the electron is spin-down and the observer has recorded down. The equation does not and cannot mix these into a single definite result, because that is not how linear equations behave. It carries both forward, fully formed, side by side. The observer who recorded up is real. The observer who recorded down is real. And each of them, looking only at their own record, is correct to say the electron had a definite spin, because relative to them, it did. That word, relative, is the whole of it. There is no absolute fact about which way the electron went. There is only what is true relative to each branch of the observer, and both branches are equally there. Part 5. The split. Let me try to put you inside the moment, because this is where the idea stops being abstract and starts being about you. Imagine you are sitting in a small, quiet room. On the table in front of you is a simple device wired to a single atom in a superposition, an atom that is genuinely poised between two possibilities. The device has a needle and a soft indicator. If the measurement comes out one way, the needle swings left and a small light glows blue. If it comes out the other way, the needle swings right and the light glows amber. You take a slow breath. You press the button to begin the measurement, and you watch. The needle swings left. The light glows blue. You see it clearly, with your own eyes, in the quiet of the room. There is no flicker of the other outcome, no ghost of amber, no sense that anything else was ever possible. As far as you can tell, the atom simply was in the left state. The measurement revealed it, and that is the end of the story. Only one thing happened. You feel completely certain of this, the same way you feel certain of everything you have ever seen. But according to Everett, in the very same instant that the needle swung left for you, something else occurred that you will never be able to detect. The measuring device, in becoming entangled with the atom, became part of the superposition, and then you, in reading the device, became part of it too. The wave function did not collapse onto the blue outcome. It developed two branches. In one of them, the needle swings left, the light glows blue, and a version of you watches it and feels certain. In the other, the needle swings right, the light glows amber, and a version of you watches that and feels exactly as certain. There was no flash, no sound, no tearing sensation, no moment where you felt yourself divide. There was simply one room, and then, soundlessly, there were two needles, two lights, one blue and one amber. Two of you, each breathing slowly, each sure they are the only one, each about to stand up and walk out of a room that the other will never enter again. Neither version is the original. That is the part that unsettles people most. You might want to ask, which one is the real you? The one who saw blue or the one who saw amber? And the answer the theory gives is that the question has no meaning. Before the measurement, there was one you, and that person had a future that contained both outcomes. After the measurement, there are two people, both of whom remember being that one person, both of whom have equal claim to being its continuation. The original did not survive as one and spawn a copy. The original became both, the way a river that reaches a fork does not send a clone down one channel while the true river takes the other. The river simply becomes two rivers, and asking which one is the real river is asking a question the world is not built to answer. And now, widen the lens, gently, because if this is true, then it is not happening only in quiet rooms with deliberate devices. Measurement, in the quantum sense, is not a special human ritual. It is just what happens whenever a quantum possibility gets entangled with something larger, and that is happening constantly, everywhere, all the time. Every time a single particle of light from the sun strikes a leaf, every time a molecule in the air bumps into another, every time an atom in your own body undergoes one of the countless quantum interactions that keep you alive, possibilities are being made to interact with the wider world, and the wave function is branching. Not once a day, not when you face a hard decision, constantly, at a rate beyond any number you could write down, in every cubic inch of space, including the space inside your own skull. The you that is listening to this sentence is, on this view, not a single thread moving through time. You are a fork in a river that has already forked more times than there are atoms in the world you can see, and that is forking again, right now, in total silence, as these words reach you. I want to sit in that small room with you a little longer, because there is a temptation to soften the idea into something cozier than it is, and the softening hides the real strangeness. You might be picturing the split as a kind of duplication, as though the universe makes a photocopy of the original you and sends it off into a side world while the real you stays here. That picture is comforting because it preserves a real you, the one true thread, with the copies as lesser shadows branching off. But that is not what the theory says, and the difference matters. There is no original left over. Before the measurement, there is one person with one future. After the measurement, there are two people, each with a complete past that includes being that one person, and neither has any better claim to being the continuation than the other. It is less like making a copy, and more like a road that simply becomes two roads, where it makes no sense to ask which fork is the continuation of the road and which is the new branch. Both are the road, both are you. And the two of you are, in that first instant, almost perfectly identical. You shared everything up to the measurement, the same childhood, the same memories, the same name, the same scar on the same knee. The only difference between you is one bit of information, one fact about which way a needle swung. But from that single shared point, the two lives begin to drift apart, because that one fact has consequences, and those consequences have consequences. The you who saw blue might mention it to a friend, who reacts a certain way, which changes a conversation, which changes a mood, which changes a decision made hours later. The you who saw amber walks a slightly different afternoon. Most of the time, the differences stay tiny, and the two worlds remain nearly twins. But every so often, a branching makes a difference that grows. The way a tiny change in the angle of a thrown ball becomes a huge difference in where it lands, until somewhere down the line, there are worlds where whole lives diverged from a single quantum coin flip that no one even noticed at the time. Now hold that image of the two of you, nearly identical, beginning to drift, and let it multiply. This is not happening once. The quantum events that drive branching are occurring constantly, in unthinkable numbers, in every object around you and inside your own body. So it is not that you split into two, and that is the end of it. You split, and each of you splits again, and again faster than any clock could mark, a constant blossoming of nearly identical selves, most of them so similar you would never tell them apart, a few of them living afternoons you can barely imagine. That blossoming is what the theory means by the many worlds. Not a tidy library of alternate histories sitting on a shelf, but a living, growing structure, branching out of every moment, including this one, as these words reach the version of you who is here to hear them. And the most disorienting part, the part we have to face next, is that you have never once felt it happen. Let yourself picture the shape of it for a moment, slowly, the way you might watch clouds change without trying to hold on to any one of them. Start with this single instant, you, here, now. From this instant, lines of possibility reach forward, most of them so close to one another that they are nearly the same line, a great soft braid of almost identical futures in which you do almost exactly what you are about to do. Here and there a strand pulls away into something more different, a future shaped by some small event swinging the other way. And every one of those strands, an instant later, does the same thing again, fanning into its own braid of nearly identical continuations, which fan again and again. There is no trunk and no single direction. There is only this endless, soundless ramifying, a structure with more branches in a single second than there are seconds in the age of the universe, and you are not standing outside it looking at the tree. You are one filament inside it, riding outward along your strand, while just beside you, closer than your own skin and forever out of reach, the other strands carry the other yous along their own quiet paths. None of them feel like branches. Each one feels exactly like this, like the single solid present you are sitting in right now. That is the picture the equation paints when you let it paint freely, and it is so far outside anything our minds were built to hold that the only honest response is a kind of stillness. So before we ask how the strangeness stays hidden, just rest for a moment in how strange it is. Part 6. Why you never feel it. The first and most natural objection to all of this is the one your whole body is probably making right now. If I am constantly splitting into countless copies, why on earth don't I feel it? Why does my experience seem so seamless, so singular, so utterly free of the sensation of dividing? This was the objection thrown at Everett from the very start, and for a long time it was the idea's greatest weakness, because Everett himself could only gesture at the answer. The full explanation did not arrive until years later, and it came from a direction nobody expected. It came from understanding, in precise detail, what it actually takes for a quantum superposition to be visible at all. Remember that the only reason we ever knew the electron went through both slits was the interference pattern, those bright and dark bands that appear when the two waves of possibility overlap and combine. Interference is the fingerprint of superposition. It is the one observable sign that more than one possibility is genuinely present and able to influence the outcome. And here is the crucial fact. Interference is extraordinarily fragile. For two branches of a wave function to interfere, they have to stay perfectly coordinated, perfectly in step, with nothing leaking out to the surrounding world that could record which branch is which. The moment any information about the system escapes into the environment, The moment a single stray particle bounces off it and carries away the news of which way it went, the interference vanishes. The branches stop being able to combine. They become, for all practical purposes, separate. This process has a name. It is called decoherence, and it was worked out, beginning in 1970, by a German physicist named Heinz-Dieter Zeh, and extended in the following decades by Wojciech Zurek and others. Decoherence is not a strange or controversial idea. It is solid, experimentally confirmed physics, accepted by essentially everyone regardless of which interpretation of quantum mechanics they favor. And what it tells us is this: the bigger and warmer and more connected to its surroundings a system is, the faster it leaks information into the environment, and the faster its superpositions decohere into separate, non-interacting branches. For a single electron in careful isolation, you can keep the superposition coherent long enough to see interference. For anything as large as a speck of dust floating in ordinary air, decoherence happens almost unimaginably fast, in something like 1/10,000,000,000th of a trillionth of a second. For something as large as a cat, or a needle, or a human brain, it is so much faster still that the word instant does not do it justice. This is the answer to why you never feel the split. You never feel it because feeling requires a brain, and a brain is a warm, wet, enormous quantum system constantly exchanging particles with its surroundings, which means it decoheres faster than almost anything. By the time any branching reaches the scale of your thoughts, the branches have already separated so completely and so irreversibly that they can never again interfere, never again combine, never again influence one another in any way. The version of you that saw blue and the version that saw amber are not just unaware of each other. They are causally sealed off from each other forever, as separate as two universes, because the one thing that could let them interact, quantum interference, was destroyed in a fraction of an instant by the sheer size and warmth of the world they live in. Each branch carries on as a complete, self-consistent, classical-looking reality, and from inside any one of them, the others simply are not there. Zurek added one more piece that makes the picture even cleaner. He showed why the branches end up looking the way they do, why we split into worlds where the cat is definitely alive or definitely dead, rather than worlds where the cat is some bizarre blur of both. The environment, it turns out, does not record every kind of quantum information equally. It naturally and ruthlessly preserves certain stable, robust states, the ones that survive constant interaction with their surroundings, and washes out the strange, blended ones almost immediately. Zurek called this Einselection, environment-induced selection, and the surviving states are sometimes called pointer states, because they are the ones a pointer on a dial can actually rest on. This is why the world you wake up in is full of definite objects in definite places, tables and cups and faces, rather than smeared quantum ghosts. The environment has already done the sorting for you, branch by branch, before your awareness ever arrives. So the strangeness does not go away, it only goes silent. Decoherence does not rescue you from the many worlds. It explains why the many worlds are invisible. It is the reason that a universe constantly shattering into countless separate histories presents itself to each of its inhabitants as a single, smooth, unbroken stream of experience. You are not spared the branching. You are simply, by the very nature of being a large, warm-thinking thing, incapable of ever noticing it. And once you understand that, the comfortable feeling that only one thing ever happens starts to look less like a fact about the universe and more like a limitation of the creature trying to perceive it. It is worth being clear about how much of this rests on solid ground and how much remains interpretation, because decoherence is sometimes oversold, and it is important to be honest. Decoherence itself is not speculation. It is established physics, worked out in mathematical detail, and confirmed in the laboratory. Experimenters have actually watched superpositions decohere in slow motion, building systems just large enough and just isolated enough that the loss of interference can be measured as it happens, like watching a struck bell go silent. We know, with confidence, that interaction with the environment destroys the ability of quantum possibilities to interfere, and we know it happens faster the larger the system. None of that depends on believing in many worlds. A physicist who thinks the wave function really collapses uses decoherence too to explain why the collapse, whatever it is, always seems to leave behind a tidy classical world. What decoherence does not do, on its own, is tell you whether the branches it creates are real. That is the line where physics hands off to interpretation. Decoherence says the branches stop interfering and become independent. The many worlds reading then says, since they are independent and the equation never removed them, they are all simply there, all real, all equally inhabited. The collapse reading says, no, only one of them is real, and the rest are removed by some process we have yet to pin down. Decoherence cannot referee between these, because both sides agree on everything it predicts. So when you hear that decoherence solves the measurement problem, take it with a little care. It solves half of it. It explains beautifully why the world looks classical and definite from the inside of any branch. It does not, by itself, tell you whether the other branches are out there. For that, you have to decide what you think the wave function is, and that decision is exactly the fork in the road that has divided physicists for almost 70 years, ever since a young man's idea was carried, with great hope, across an ocean, to the one person whose blessing might have changed everything. Part 7. Bohr's Wall. When Everett finished his doctoral work in 1957, he believed he had solved one of the great problems of physics. He had taken the ugly two-rule structure of quantum mechanics and replaced it with a single clean law, and in doing so he had explained the appearance of collapse without needing collapse to be real. His original manuscript, a long and careful piece of work, carried the grand title, The Theory of the Universal Wave Function. It was the work of a young man who thought he was about to change everything. What happened next is one of the quietly heartbreaking stories in the history of science. The problem was Niels Bohr. By the 1950s, Bohr was not just a physicist. He was an institution, the elder statesman of quantum theory, the man whose Copenhagen interpretation had become the orthodox view taught in every university. To question collapse was, in effect, to question Bohr, and the world of physics had arranged itself around the assumption that Bohr had already settled these questions decades earlier. Everett's advisor, John Wheeler, greatly admired Bohr, and he was caught in an awkward position. He could see that his student's work was serious and original, but he also did not want it to read as an attack on the man he revered. So Wheeler pushed Everett to soften the manuscript, to trim its boldest claims, to make it more palatable. The long thesis was cut down to a fraction of its size. The dramatic language was muted. The published paper that finally appeared in 1957 was a pale, compressed shadow of what Everett had originally written, and even then, the world of physics mostly met it with silence. In 1959, Everett travelled to Copenhagen, hoping to win Bohr over in person. It should have been the meeting that vindicated him. Instead, it was a disaster. Bohr and his circle were not interested in reopening questions they considered closed. The conversations went nowhere. One of Bohr's close associates, the physicist Leon Rosenfeld, later described Everett in private with open contempt, calling him hopelessly confused about the most basic principles of quantum mechanics. The young man who had come to share what he thought was a profound discovery was treated, by the people he most wanted to impress, as a naive student who simply did not understand the subject. There was no debate to be won, because the people on the other side did not consider his idea worth debating. He had run straight into a wall, and the wall did not move. Everett never really recovered from that rejection, at least not as a physicist. He had already begun working outside academia, and after Copenhagen, he turned away from fundamental physics almost entirely. He went to work for the defense establishment, applying his formidable mathematical mind to the cold calculus of nuclear war. He worked for the Pentagon's Weapons Systems Evaluation Group and later founded private companies doing operations, research, optimization, the mathematics of targeting and strategy. He was, by all accounts, very good at it, and he made a comfortable living. But the man who had glimpsed the universal wave function spent the rest of his career calculating fallout patterns and weapons effectiveness, and he rarely spoke about the idea that should have made his name. He smoked and drank heavily, he gained weight, and he carried, beneath a layer of dry humor, the quiet bitterness of someone who believed he had been right and had not been heard. This is the human cost that sits underneath the physics, and I do not want to rush past it, because it is part of what the idea means. Here was a person who, at 26 years old, may have seen further into the structure of reality than almost anyone of his generation, and who was told, by the very people best equipped to understand him, that he was simply confused. He was right too early, in a world that was not ready to hear it, and being right too early can be almost indistinguishable from being wrong, because the result is the same. You are not believed. The idea goes into a drawer, and the person who carried it learns to stop bringing it up. Everett would not live to see his vindication. He died in 1982, suddenly, of cardiac arrest, at the age of 51. He had asked that after his death his remains be discarded with the trash, and his wishes were honoured. The man who imagined infinite worlds wanted, for himself, to simply be thrown away. We will return to his family later tonight, because the story does not end with him, and what came after is even harder to hold. But first we have to follow the idea itself, because while Everett was calculating weapons effects in obscurity, something was beginning to stir. Let me set the Copenhagen meeting before you as a scene, because it is one of the quietly tragic moments in the history of science, and it deserves to be felt rather than just summarized. It is the spring of 1959. Everett is not yet 30. He has crossed the ocean carrying the thing he believes is the most important idea of his life, and he has come to the one place that could give it a future, the institute in Copenhagen, where Niels Bohr presides over the temple of quantum theory. Picture the room. There is coffee and pipe smoke, and the particular politeness of men who have already decided you are wrong. Everett begins to explain. He talks about the universal wave function, about taking the equation seriously, about the observer being part of the system, about the branching that follows. And as he talks, he watches the faces, and he sees not curiosity, but a kind of weary patience, the look people give a young man who has not yet understood why his clever idea cannot possibly be right. Bohr is courteous and immovable. The conversation circles and goes nowhere. No one shouts. No one is cruel to his face. It is gentler than cruelty, and worse than cruelty. It is dismissal. Everett leaves Copenhagen with nothing, and somewhere on the journey home the door to his life as a physicist quietly closes, and he lets it close. What he turned to instead has its own grim significance. Everett took his brilliance to the American defense establishment, into the world of nuclear strategy and operations research. He worked on the mathematics of how nuclear weapons might be targeted and how their effects might be calculated, the cold arithmetic of fallout and casualties and deterrence. There is a dark irony in it that is hard to miss. The man who had imagined a reality where every possibility comes true spent his working life calculating the probabilities of the worst possibility of all, the one we have so far managed not to make real. He was good at it. He helped develop mathematical methods that are still used in optimization today. He grew prosperous. But the part of him that had seen all the way to the structure of reality, went quiet and stayed quiet for the rest of his life. He almost never published on physics again. The greatest idea he ever had became, for him, a thing he had done once, long ago, that nobody wanted. Part 8. Do you feel the earth moving? An idea can be buried, but if it is true, or even just strange enough, it has a way of refusing to stay buried. While Everett had walked away from physics, his thesis had not entirely vanished. It sat in the literature, mostly unread, occasionally stumbled upon by someone curious enough to take it seriously. And in 1970, more than a decade after the idea had been dismissed in Copenhagen, it found the champion it had been waiting for. His name was Bryce DeWitt, an American physicist with a taste for bold ideas and a gift for vivid writing, and he did two things that changed the fate of Everett's work forever. He gave it a name, and he refused to be embarrassed by it. The name was the one we have been using all night. DeWitt called it the Many Worlds Interpretation, and he wrote about it in an article in the magazine Physics Today that landed like a small explosion among physicists who read it. He laid out Everett's logic plainly, and then he leaned into its most shocking consequence rather than shunned away from it. He wrote about the universe constantly splitting into countless copies of itself, about every quantum transition on every star branching the cosmos into uncountable versions, and he did not apologize for how strange it sounded. He treated the strangeness as a feature of the truth, not a reason to look away. The phrase many worlds was dramatic, almost lurid, and it did exactly what a good name does. It made the idea impossible to ignore. A few years later, in 1973, DeWitt and a colleague, Neil Graham, published a book collecting Everett's full original thesis alongside supporting papers, finally putting the long, uncut version of the argument into the hands of physicists everywhere. The idea that had been compressed and silenced in 1957 was back in full under a name no one could forget. DeWitt was honest about his own first reaction, and it is the same reaction almost everyone has, including, probably, you. When he first encountered Everett's idea, he objected that he simply could not feel himself splitting into multiple copies. The notion was offensive to common sense. He could not sense any branching, any division, any moment where his single stream of experience forked into many, and the response he received, the response that reportedly changed his mind, is one of the most elegant turns in this entire story. The reply was a question: do you feel the earth moving? Think about what is buried in that question. You are, right now, sitting on the surface of a planet that is spinning at hundreds of meters per second and racing around the sun at about 30 kilometers every second, which is something like 100,000 kilometers per hour. You are hurtling through space at a speed that defies comprehension, and you feel absolutely none of it. You feel perfectly still. For most of human history, this stillness was taken as obvious proof that the earth did not move, that it sat fixed at the center of creation while the heavens turned around it. The idea that the ground beneath your feet was actually tearing through space at enormous speed seemed not just wrong, but absurd, contradicted by the plain evidence of your own body. And yet it is true. The earth does move. Your failure to feel it is not evidence that it sits still. It is evidence that human senses were never designed to detect that kind of motion, and so they simply do not. The many worlds argument turns this exact lesson on the question of the splitting self. Of course, you do not feel yourself branching. There is no reason you should. Each version of you, after a split, carries a complete and consistent set of memories and sensations, and finds itself in a single coherent world, exactly as it would if no branching had occurred. There is no internal signal of division, no jolt, no doubling of sensation, because each branch contains a whole observer who who experiences only that branch. The absence of any feeling of splitting is not evidence against the splitting. It is precisely what the theory predicts you would experience, whether or not the splitting is real. And just as we eventually learn to trust the mathematics of a moving Earth over the testimony of our motionless feeling bodies, the many worlds defenders argue we should be willing to trust the mathematics of an unbroken wave function over the testimony of our singular feeling selves. Common sense told us the Earth was still. Common sense was wrong. It would not be the first time the universe turned out to be doing something enormous that we were simply built not to notice. The Copernican comparison runs even deeper than the question DeWitt was asked, and it is worth following, because the history of science is in some ways a long series of these same lessons, each one taking something away from the center of the picture, and each one resisted fiercely at the time. When Copernicus suggested the Earth went around the Sun rather than the other way, the objection was not only that we cannot feel the motion, it was that the idea seemed to demote us, to take the Earth out of its special place at the center of everything and make it just one more planet among others. People did not want to be one planet among many. It felt like a loss, almost an insult. And yet it was true, and we survived the truth. And in time, the larger universe it revealed turned out to be more wonderful than the small closed one it replaced. The same thing happened again when we learned the Sun was just one ordinary star among hundreds of billions, and again when we learned our galaxy was just one among hundreds of billions of galaxies. Each step took us further from the center, and each step was resisted, and each step turned out to be right. The many worlds interpretation, its defenders argue, is simply the next step in that long demotion, the deepest one yet. It takes our world, the single reality we were sure we lived in, and makes it one branch among countless others. And just as before, the idea feels like a loss. It seems to cheapen our world, our choices, our very selves, by multiplying them endlessly. But the people who hold the idea say that this feeling too is just the old resistance in a new form, the same instinct that did not want the Earth to move, now not wanting the world to branch. They would say that if the universe is genuinely this large, this strange, this full of unseen reality, then our discomfort is not an argument against it, any more than vertigo is an argument against the height of a mountain. The question is not whether the idea makes us comfortable. The question is whether it is what the equations, read honestly, actually say. And that brings us to the hardest part of the whole story, the part where we have to stop admiring the idea and start counting its costs. Because a theory this bold does not come cheap, and an honest mind has to look squarely at the bill. It is worth saying, before we count those costs, just how far the idea has travelled since DeWitt pulled it out of obscurity, because the journey itself tells you something. In the 1950s, it was a single rejected thesis. By the 1970s, it had a name and a champion and a book. And in the decades since, it has gathered around it some of the most capable thinkers in physics and philosophy, people who have devoted careers to working out its details rather than just admiring its boldness. The physicist David Deutsch, one of the founders of the entire field of quantum computing, built much of his life's work on taking the many worlds literally. The philosopher David Wallace wrote a careful, demanding book defending the interpretation as the most reasonable reading of quantum mechanics we have. The physicist Sean Carroll has argued for it in technical papers and in books written for everyone, treating it not as science fiction, but as the plain consequence of trusting our best equation. The cosmologist Max Tegmark folded it into a grand picture of layered parallel universes. These are not cranks on the margins. They are working scientists at major institutions, and they hold this view not in spite of their rigor, but they would say because of it. That does not make the idea correct. Plenty of brilliant people have been confidently wrong, but it should put to rest any notion that many worlds is a fringe fantasy. It is a serious, mainstream, minority position, argued for in the open by people who understand the mathematics as well as anyone alive, and the fact that they cannot persuade the majority and the majority cannot refute them is itself one of the most telling facts about where physics actually stands. We have a theory that works perfectly and a room full of geniuses who cannot agree on what it is telling us about reality. That disagreement is not a sign of failure. It is a sign that we have run into something genuinely hard. Part 9. The bill comes due. It would be dishonest of me to make this idea sound like a clean victory, because it is not. The many worlds interpretation solves the measurement problem with remarkable economy, but it does not get that economy for free. It trades one set of hard problems for another, and any honest account has to lay the bill on the table. The defenders of this idea are not naive enthusiasts. They are serious physicists and philosophers who have spent decades wrestling with exactly these difficulties, and the back and forth between them and their critics is some of the sharpest argument in all of modern physics. So, let us be fair to both sides, because the real story is not a triumph. It is a genuine fight that is still going on. The first objection is the one that probably occurred to you several parts ago, and it is usually phrased in terms of a principle called Occam's razor, the old rule of thumb that says, when choosing between explanations, prefer the one that assumes the least. And on the face of it, nothing could be more extravagant than a theory that postulates an uncountable infinity of entire universes, each as large and full as our own, branching endlessly forever. How could that possibly be the simple option? It seems like the most bloated, wasteful, absurdly excessive picture of reality anyone has ever proposed. Surely Occam's razor slices it to ribbons. This is the most common gut reaction, and it is a powerful one. The Everettians have an answer, and whether you find it convincing is one of the genuine forks in this debate. They argue that Occam's razor is about the simplicity of your assumptions, not the size of what those assumptions produce. The many worlds theory makes fewer assumptions than any rival. It assumes only the wave function and the Schrödinger equation, nothing more. The many worlds are not an added assumption. They are an unavoidable consequence of those minimal ingredients. By contrast, the Copenhagen view has to add an extra rule, the collapse, a rule nobody can define or locate, just to throw away the worlds the equation produces. So, which is really simpler, they ask? A spare theory with extravagant consequences, or a cluttered theory with comfortable ones? The worlds, they insist, are cheap. It is the collapse that is expensive. The second objection is subtler, and, to many physicists, far more serious. It is the problem of probability, and it cuts at something we have been quietly assuming all night. Quantum mechanics does not just say that different outcomes can happen. It assigns precise probabilities to them, and those probabilities are confirmed by experiment to staggering accuracy. The rule for calculating them, called the Born rule, after the physicist Max Born, who wrote it down in 1926, says that the probability of an outcome is given by the square of the size of its piece of the wave function. Some outcomes are more likely, some less, and the numbers come out exactly right every time. But here is the real trouble for many worlds. If every outcome actually happens, in its own branch, with certainty, then what could it possibly mean to say one of them is more probable than another? They all occur. There is a version of you for each. How do you fit the idea of probability, of one thing being likelier than another, into a picture where everything definitely happens? This is not a small wrinkle. For a while it looked like it might be fatal, because a theory of physics that cannot recover the very probabilities that physics is built on is a theory in serious trouble. The Everettians have fought hard to answer it, and they have produced two main lines of response, both ingenious and both still argued over. The first came from David Deutsch in 1999, and was developed further by the philosopher David Wallace. They approached it through decision theory, the mathematics of rational betting. They tried to show that a rational person who fully believed in branching and who had to place bets on quantum outcomes would be forced, by pure logic, to bet exactly as if the Bohr rule probabilities were true, even though every outcome was going to happen. In other words, the Bohr rule emerges not as a statement about how often things occur, but as the only rational way to care about your many future selves. The second line of response came from the physicist Sean Carroll and his collaborator Charles Seabans around 2014, and it leans on a beautiful idea called self-locating uncertainty. In the brief instant after a branch has formed, but before you have looked at the result, there are now two of you, and neither one yet knows which branch they are in. Each is genuinely uncertain about their own location in the universe, about which copy they happen to be. And when you carefully work out how a rational person should reason under that very specific kind of uncertainty, the Bohr rule probabilities fall out once again. Critics counter that both of these derivations quietly assume part of what they are trying to prove, and the debate over whether the Bohr rule has truly been explained or merely redescribed has not been settled. It is, right now, one of the live frontiers of the entire subject. The point I want you to take from this is not that many worlds has won, and not that it has lost, but that it is a real contender, defended by formidable people, fighting real objections in the open. This is not fringe. This is physics arguing with itself about what its own equations mean. There are two more objections worth knowing, because they show how the idea has been pressured and how it has answered. The first is sometimes called the preferred basis problem, and it sounds technical, but the worry underneath it is simple. If the world is constantly branching, why does it branch into the particular kinds of worlds we actually experience? Why do we split into a world where the cat is alive and a world where it is dead, rather than a world where the cat is some strange combination of alive and dead that we have no word for? The mathematics, taken raw, does not obviously prefer the alive or dead way of slicing things up over the bizarre blended way. So, what picks the slices? For years, this was a genuine soft spot in the theory. The answer, when it came, was the very decoherence we met earlier. The environment, it turns out, does not record the bizarre blended states. It naturally and relentlessly singles out the stable, ordinary states, the ones robust enough to survive constant battering by stray particles, and those stable states are exactly the alive or dead kind. So the branches we end up in are not chosen arbitrarily. They are selected by the physics of the environment, which only ever keeps the kinds of worlds that can hold together. The soft spot, it turned out, was filled by physics that had been discovered for entirely separate reasons. The second remaining objection is the one people find most maddening, and it is the question of number. How many worlds are there? The instinct is to demand a count, a figure, even an enormous one. Bryce DeWitt himself, in his enthusiasm, once spoke of more than 10 to the 100th power of branches, a 1 followed by 100 zeros, which is already a number larger than the count of every atom in the visible universe. But the modern view is stranger and, in a way, more humbling. It says the question may not have a sharp answer at all. Branching is not a tidy clicking process where you can stand outside and tally each new world as it forms. It is a continuous, fuzzy, ongoing affair, more like asking how many distinct gusts there are in a long wind than how many coins are in a jar. The worlds are real on this view, but they are not discrete objects with a fixed inventory. They are emergent patterns within one smooth, continuous wave function, the way ripples are real features of a pond, without the pond being made of a definite number of separate ripples. To a critic, this fuzziness is a scandal. A theory that posits countless worlds, but cannot say how many, or even whether how many is a real question, sounds like it is hiding behind vagueness. To a defender, it is simply honesty about a continuous reality that was never built to be counted on our fingers. Either way, it leaves you with one of the most disorienting facts in all of physics. If this idea is true, then the most personal question you could possibly ask, how many of me are there, may have no answer, not because we are not clever enough to find it, but because the universe is not the kind of thing that keeps that particular tally. It is worth lingering on why the probability problem is treated as the truly serious objection, more serious than the worries about extravagance or counting, because it reveals something about how science actually weighs ideas. Physics is, at its core, a machine for making predictions and checking them against the world, and the predictions of quantum mechanics are all probabilistic. When a physicist says an experiment will give one result 70% of the time and another result 30% of the time, and then runs it thousands of times and watches the results pile up at exactly 70 and 30, that agreement is the entire reason we trust the theory at all. So any interpretation that cannot make clean sense of those percentages is not merely inelegant, it is in danger of cutting the cord that connects the theory to evidence in the first place. That is why the Everettians have poured so much effort into the problem, and why their critics watch that effort so closely. If the only way to recover the Bohr rule inside a branching universe is to quietly assume the very thing you are trying to explain, then the derivation is circular, and the theory has not earned its predictions, it has borrowed them. If, on the other hand, the decision-theoretic and self-locating uncertainty arguments really do work, then something close to a miracle has occurred. A theory in which everything definitely happens has reproduced, from the inside, the exact pattern of probabilities we measure, which would be a powerful point in its favour. Where the truth lies in that argument is still genuinely open, and reasonable experts still disagree, which is exactly why it remains one of the most active questions at the foundations of physics, rather than a settled matter in a textbook. And once the arguing over costs and counts has run its course, the same unavoidable question rises up that hangs over every interpretation of quantum mechanics. Is there anything we could actually do, any experiment we could actually run that would tell us whether the other worlds are really out there? Part 10. Where is the number factored? If the many worlds interpretation can never be felt from the inside, and if its rivals make exactly the same predictions in every experiment, a fair person is entitled to ask the hardest question of all. Is there any reason to believe it beyond mathematical elegance? Is there anything in the actual world that points toward the other branches being real, rather than just a poetic way of talking about the equations? The honest answer is that there is no direct proof, and there may never be one, for reasons we will come to. But there is one argument that comes closer than any other to putting a finger on something physical, and it comes from David Deutsch, one of the founders of the field of quantum computing. Deutsch's argument runs like this. A quantum computer is a machine that exploits superposition to perform certain calculations far faster than any ordinary computer ever could. There is a famous algorithm discovered by the mathematician Peter Shaw that lets a quantum computer find the factors of enormous numbers, the kind of problem that would take an ordinary computer longer than the age of the universe for a large enough number. Now imagine you actually build such a machine and run Shaw's algorithm on a number so large that factoring it would require more individual computational steps than there are atoms in the entire visible universe. The machine hums for a while, and out comes the answer, the correct factors. And Deutsch asks a simple, almost childlike question that is surprisingly hard to dismiss. Where, physically, was that calculation carried out? There were not enough particles in the observable universe to hold all those computational steps at once. So where did the work actually happen? Deutsch's answer is that the computation was shared across the branches. The quantum computer, by holding its information in superposition, was effectively running the calculation in parallel across an enormous number of nearly identical versions of itself, In an enormous number of nearly identical worlds, each doing part of the work, all of them combining their results at the end into the single answer you read off the screen. To Deutsch, the staggering power of quantum computing is not a clever trick of the mathematics. It is the many worlds making themselves useful, the parallel universes pooling their effort to solve a problem no single universe could solve alone. He has put the challenge bluntly to his critics. If the visible universe does not contain enough resources to perform the calculation, and the calculation is nonetheless performed, then where do you think it happened? Most physicists do not accept this as proof, and they point out, correctly, that the same results can be derived from the mathematics without ever committing to literally real worlds. But Deutsch's question lingers, because it reframes the whole debate. Whatever you choose to call them, the parallel paths are doing real computational work in the equations. The argument is over whether to read that work as a manner of speaking or as a description of something out there. There is a second reason serious physicists are drawn to many worlds, and it is less about evidence and more about what the theory quietly gives back. Ordinary quantum mechanics, with its collapse, has two features that have troubled physicists since the beginning. The first is that it is random. Collapse picks an outcome by genuine chance, which means the universe, at its foundation, contains irreducible randomness, a dice roll that not even God, in Einstein's famous complaint, should be playing. The second is that it appears to be non-local. In experiments with entangled particles, measuring one particle seems to instantly affect the state of its distant partner, no matter how far apart they are, a connection that troubled Einstein so much he called it spooky action at a distance, and which the physicist John Bell, in 1964, proved was a real and unavoidable feature of the predictions. Both of these, the randomness and the spooky connection, are profoundly uncomfortable. They sit awkwardly with everything else we know about how the universe behaves. The many worlds interpretation makes both of them disappear. Because nothing ever collapses, nothing is ever truly random. The universal wave function evolves with perfect clockwork determinism, exactly as the Schrödinger equation says. And the only reason the world looks random to you is that you cannot predict which branch you will find yourself in, since there will be versions of you in all of them. The apparent randomness is just your ignorance about your own location among your future selves. And the spooky action vanishes too, because nothing needs to be coordinated across the distance. When you measure one entangled particle, you simply branch locally, and your distant partner branches locally when their measurement happens, and the correlations line up perfectly when the two of you finally compare notes, with no faster-than-light signal ever having to pass between you. For its defenders, this is the real prize, larger even than solving the measurement problem. Many worlds takes the two ugliest features of quantum mechanics, its randomness and its non-locality, and reveals them as illusions produced by living inside a single branch. It makes the quantum world obey the same calm, local, deterministic rules as the rest of physics. The cost is the worlds. The question every physicist has to answer privately is whether that price is too high or whether it is the bargain of the century. And yet, for all its elegance, the theory runs into a wall that no amount of cleverness has been able to break. The branches, once they decohere, can never again interact. That is not a temporary limitation of our instruments. It is built into the physics. The very decoherence that explains why the worlds are separate also guarantees that no experiment, ever, even in principle, could let you reach across to another branch and confirm it is there. The other worlds are not far away in space. They are not hidden behind a barrier we might one day tunnel through. They are sealed off by the structure of reality itself, which means the many worlds interpretation makes a prediction it can never test, claims the existence of things it can never show you, and asks you to believe in an infinity of universes on the strength of an equation and an argument. To some, that makes it not science at all, but metaphysics wearing the clothing of physics. To others, it makes it the most honest theory we have, the one brave enough to say what the mathematics plainly implies and accept that we are simply not positioned to see the rest. That tension between a theory that explains everything and proves nothing is where the idea lives, and where it will likely stay for a very long time. To see why this question is so hard to escape, it helps to know that many worlds is not alone on the field. It is one answer among several to the same measurement problem, and the others are held by serious people for serious reasons, and crucially, they all make the same predictions for every experiment we know how to do. That last fact is the whole difficulty in a single sentence. Let me lay out the main contenders, because seeing the menu is the only way to feel how genuinely stuck we are. The standard textbook view, Copenhagen, says the collapse is real and fundamental, and that you simply should not ask what happens between measurements. It is the most widely taught, and, to its critics, the least satisfying because it leaves the central process undefined. Then there is the pilot wave theory, sometimes called Bohmian mechanics, after the physicist David Bohm, which says that particles really do have definite positions at all times, guided along by a real, physical wave. It is fully deterministic and keeps a single world, which sounds wonderful, but it pays its own price. To match experiment, the guiding wave has to be explicitly non-local, with distant parts of the universe instantly influencing one another. The very spookiness that troubled Einstein, now built into the foundation on purpose. There is a third family, the objective collapse theories, and these are the most interesting from the standpoint of testing, so they are worth singling out. The best known was proposed in 1986 by three physicists, Girardi, Rimini, and Weber, and the British mathematician Roger Penrose has argued for a version driven by gravity. These theories say the collapse is real, just as Copenhagen does. But unlike Copenhagen, they say it is a genuine physical process that happens spontaneously, on its own, with a tiny probability per particle per moment, a probability so small that a single atom almost never collapses, but a large object, made of countless atoms, collapses almost instantly. The beautiful thing about these theories is that they make slightly different predictions from ordinary quantum mechanics in just the right delicate experiments, which means they can, in principle, be tested and ruled out. Experimenters are right now pushing larger and larger objects into superposition, trying to catch a collapse in the act, and so far they have not found one, which quietly tightens the noose on those models. And finally, there is a family of views, sometimes grouped under the name cubism, that say the wave function is not a thing in the world at all, but a description of an observer's knowledge, so that collapse is nothing more dramatic than you updating your beliefs when you learn a new fact. Notice what this menu means. Pilot wave, objective collapse, cubism, and many worlds all reproduce the same laboratory results, at least everywhere we have so far been able to look. They are not competing theories in the usual sense, where one predicts something the others do not, and an experiment decides between them. They are competing stories about what the same equations mean, what is actually real behind the same predictions, and many worlds occupies a particular position on that menu. It is the only one that keeps the equations completely untouched, adding nothing and removing nothing, accepting whatever they imply. Its defenders see that as its great virtue, the reason to prefer it. Its critics see the unobservable worlds as the reason to look elsewhere. Max Tegmark has even argued that the branching worlds of this theory are just one example of a larger pattern, fitting them into a tiered picture of parallel universes, alongside regions beyond our cosmic horizon and the bubble universes of cosmic inflation, all of them different routes, to the same unsettling conclusion that ours is not the only world, but whichever way you lean, the the menu makes one thing brutally clear. Choosing among these is not, at least for now, something an experiment can do for you. It is something you have to do for yourself, with reason and taste and a tolerance for strangeness, and that is a profoundly uncomfortable place for a science to find itself. This is the point where the sharpest critics make their stand, and their objection deserves a fair hearing because it cuts to what science even is. There is a long tradition in physics, associated with the philosopher Karl Popper, that says a claim only counts as scientific if there is some conceivable observation that could prove it false. A theory that can absorb any result, that predicts the same thing no matter what you see, has stepped outside the boundary of science and into something else. And by that standard, the critics say, many worlds is in real trouble. If the other branches can never, even in principle, be detected, then claiming they exist is not a scientific statement at all. It is a story laid on top of the equations, no more testable than a claim about what lies beyond the edge of the observable universe. The defenders have a reply, and it is a thoughtful one. They point out that many worlds is not a separate theory bolted onto quantum mechanics. It is just quantum mechanics, taken literally with nothing added. Every experiment that tests quantum mechanics tests many worlds because they are the same equations. What is untestable is not the physics, but one particular question about it, namely whether the branches the equations describe should be called real, and they turn the charge around. The collapse, they say, is the thing that was added without evidence, an extra process no one has ever observed, invented purely to make the unwanted worlds go away. So which is less scientific, they ask, accepting what the tested equation says, or postulating an unseen mechanism to delete part of what it says? There is no clean winner in this exchange, and that is rather the point. The argument over many worlds is not really an argument inside physics. It is an argument about what physics is for, about whether our job is only to predict what we will see, or also to say what is actually there behind the predictions. Those are different ambitions, and people who share every equation can still part ways over which one matters more. That is why this debate has lasted 70 years and may last 70 more, and why no single experiment is going to end it. Part 11. The branch where you survive. There is a corner of this idea that people find almost impossible to leave alone once they have heard it, and I want to walk into it slowly and carefully, because it is the place where the abstract physics presses hardest against real human fear. It is a thought experiment, usually called quantum suicide, or in its gentler form, quantum immortality, and it was laid out most clearly by the physicist Max Tegmark in the late 1990s. I want to be clear before we begin that it is a thought experiment, a tool for thinking, and nothing more. It is not advice, and as you will see, even on its own terms, it offers no comfort that survives a second look. But it shows you, better than anything else, just how strange the many worlds picture becomes when you push it all the way to its edge. Here is the experiment, kept entirely in the mind. Imagine a device wired to a quantum event, the same kind of fundamentally uncertain coin flip we met earlier, set up so that each time it is triggered, there is a 50-50 quantum outcome. Imagine the device is arranged so that one outcome is harmless and the other is fatal, instantly and painlessly. Now imagine triggering it, again and again. From the perspective of someone watching from outside, the story is grim and ordinary. They see you survive the first trigger with even odds, and the second, and perhaps the third, and then, on some trigger, they see the fatal outcome arrive, and they watch you die, and they grieve. That is what the outside observer experiences in their branch, and it is exactly as awful as it sounds. But now consider the experiment from the inside, from your own stream of awareness. Every time the device triggers, the world branches. In one branch you are gone, and there is no you left there to experience anything at all. In the other branch, you survive, and your awareness, by definition, continues only there, because that is the only branch in which there is a you to continue. So from the inside, you never experience the fatal outcome. You only ever find yourself, again and again, in the branch where you happen to live. Trigger after trigger, you keep waking up, improbably, impossibly, always on the surviving side, because the side where you did not survive contains no one to notice. Followed to its conclusion, the thought experiment suggests that from your own point of view, you might never experience your own death at all. It is a genuinely vertiginous idea, and it is easy to see why it grips people, especially anyone who has lain awake afraid of dying. But step back into the wider picture, the way Tegmark himself insists you must, and the false comfort drains away. For every branch in which you keep waking up, there are all the branches in which you did not, and those branches are just as real, and they are full of the people who loved you, standing in rooms that now have your absence in them. Your subjective thread may slip from surviving branch to surviving branch, but you do so by leaving a trail of grief behind you in every world you fall out of. There is no version of this where everyone is spared. There is only a version where the one consciousness following along happens never to be in the room when the worst happens. And the idea rests on assumptions about the nature of personal identity, about what it even means for your experience to continue, that are nowhere near as solid as the thought experiment makes them sound. This is why no serious physicist treats it as a reason to do anything at all. It is a flashlight pointed into the strangest cave of the theory, showing you how alien the terrain becomes out there. It is not a door you are meant to walk through. The reason the thought experiment falls apart as anything more than a curiosity is that it leans on assumptions about the self that nobody can actually defend. It assumes that your stream of awareness is a single thing that must continue somewhere, that it will always flow into a surviving branch the way water finds the open channel. But the theory gives no special status to your awareness at all. In the branches where the outcome is fatal, there is simply no one there, no perspective left over, no thread waiting to be rerouted. It is not that your awareness leaps to safety. It is that one branch contains a living you and the other contains your absence, and there is no rule in the physics that says the living one is more truly you than the gap. The whole spell of quantum immortality comes from quietly imagining yourself standing outside the branches, choosing to identify only with the survivor, and that vantage point does not exist. There is no you above the branching, picking which copy to be. There are only the copies, and some of them are not there. This is exactly why Max Tegmark, who laid the idea out most clearly, has always insisted it is a thought experiment and never a plan. He has said plainly that he does not believe it offers any comfort and would never act on it, and that its real value is to expose how strange our ordinary assumptions about identity and probability become once branching is taken seriously. It is a tool for finding the soft places in our thinking, not a discovery about how to cheat death, and it carries a hidden cruelty that the cheerful version always omits. Even if your own thread did somehow always continue, you would be doing so alone, watching everyone you love eventually fall away into the branches you slipped out of, becoming the one survivor at an endless series of funerals you never have to attend, only because you are always, by chance, in the next room. That is not immortality as anyone would wish for it. It is the loneliest possible reading of a lonely idea, and it is one more reason to treat the many worlds with wonder rather than longing. I tell you all of this because the man who started this entire story lived close to these questions in a way that is almost unbearable to think about. Hugh Everett believed his theory was true. He believed it literally, all the way down, including, those close to him have suggested, its implications for death. If every outcome happens, then in some branch you always continue. And there are accounts that Everett took a private, fatalistic comfort in this, that he did not fear his own end the way most people do, because he did not believe, in the deepest sense, that it was an end. When he died in 1982, suddenly, at 51, he left behind a son and a daughter. His son, Mark, grew up to become a musician, and years later he made a quietly devastating documentary trying to understand the father he had barely known, traveling to meet the physicists who finally took his father's work seriously, learning only after the man was gone that the distant, difficult figure from his childhood had imagined a universe of infinite worlds. And then there is Everett's daughter, Elizabeth. I am going to speak about this gently, because it is the most painful consequence of the idea, and it deserves to be held with care rather than used for effect. Elizabeth struggled for many years, and in 1996 she took her own life. She left a note, and in that note she wrote that she was going to find her father, that she was going, in some sense, to another universe to be with him. A grieving young woman reached, in her darkest moment, for the one idea her father had given the world, and she took it not as physics, but as a kind of promise, a door to a place where the family might be together in a way it never managed to be here. I do not raise this to draw a tidy lesson from it, because there is none. I raise it because it is the truest measure of how heavily this idea can land on a real human life. The many worlds began as marks on a chalkboard, a way of reading an equation honestly. But ideas do not stay on chalkboards. They travel into the lives of the people who hold them, and they can become, for better and for worse, the stories we tell ourselves about loss and survival, and whether goodbye is ever really final. If you are listening tonight, and any of this sits close to your own life, let it be a reminder that whatever the equations say about other worlds, the people beside you in this one are the ones who can actually reach you. Part 12. Only One World. We began, a long while ago now, with a small and ordinary moment, a choice you made earlier today, a drink you poured, a road you took, and the quiet certainty that came with it. Only one thing happened. I asked you to hold on to that phrase, and now, at the end, I want to hand it back to you, turned all the way around. Because if Hugh Everett was right, then only one thing happened to you, but not only one thing happened. The drink you didn't pour was poured. The road you didn't take was taken. The word you swallowed was spoken, out loud, in a room as real as the one you are in now, by a person who is, in every meaningful sense, you. They are not a copy of you, and you are not the original. You are two branches of the same river, and the only difference between you is which way the water happened to go. Let me be honest one more time about what the title promised, and what the physics actually delivers, because the gap is where all the wonder has been hiding. What if every choice splits the universe? The truth is that your choices are not what does the splitting. The universe is not waiting on your decisions, dividing itself politely each time you hesitate at the refrigerator. It is branching constantly, at a rate beyond counting, driven by the behavior of particles far beneath the level of anything you would call a decision, and it would go on branching exactly the same way if there were no one in it to choose anything at all. Your choices ride on top of that endless branching like a leaf on the surface of a river that was already splitting into 1,000 channels. And yet, in a strange way, the romantic version of the title becomes true again at the end, because whatever the cause, the consequence is real. Every road you could have taken is a road that some version of you is walking right now. The branching is not about your choices. But your choices, like everything else, branch. This is the part where you might expect me to tell you whether it is true, and I cannot, and neither can anyone else, and that is not a failure of mine or of physics. It is the honest situation. The many worlds interpretation might be the deepest reading of reality anyone has ever achieved, the moment we finally learn to take our own equations at their word. Or it might be a beautiful overreach, a case of mistaking the richness of the mathematics for the structure of the world. The other interpretations are still standing. Some physicists think the wave function really does collapse. Some think particles have definite positions guided by a hidden wave. Some think the whole thing is just information in our heads. They all predict the same experiments every time, which is exactly why we cannot use experiments to choose between them. You are left, as we all are, having to decide what to believe about a part of reality that has been arranged by its own nature so that no one inside it can ever look and check. You might wonder what difference any of this should make to how you live, and it is a fair thing to ask at the end of a long night. If the worlds are real but sealed away forever, if you can never reach them or even prove they are there, then in one obvious sense, nothing changes at all. You will still wake up tomorrow in this branch, the only one you will ever know, and the cup of coffee will still be warm, and the floor will still be solid, and the people you love will still be exactly where you left them. The many worlds, if they exist, do not lighten your responsibilities or excuse your choices. Some people, on first hearing the idea, worry that it makes everything meaningless, that if every choice happens somewhere, then no choice matters here. But that gets it backwards. The other branches are not yours. You do not experience them. You cannot help the versions of you in them, and they cannot help you. The only world your choices shape, the only one you will live in and answer for, is this one. The branch you are in is still the whole of your life. That a different you, in a world you will never touch, made a different call, changes nothing about the weight of the call you make tonight. There is something else the idea quietly offers, though, if you are willing to hold it gently. It is a particular kind of peace about the roads not taken. Every one of us carries a small museum of regrets and what-ifs, the job we turned down, the person we did not call, the chance we let pass, the words we wish we had said or not said. We tend to imagine those alternatives as ghosts, as nothing, as the empty dark where a different life might have been. The many worlds picture, true or not, suggests another way to hold them. Perhaps those lives are not ghosts. Perhaps somewhere, in a branch as real as this one, the version of you who made the other choice is living it out, and it is neither better nor worse than yours in any way you are entitled to envy, just different, just another thread of the same person. You do not have to live those lives. You are never going to live all of them. You only ever had to live one, the one that is yours, and the others are not lost, because they were never yours to lose. There is a strange comfort in that, a way of setting down the heavy idea that you should somehow have been all your possible selves at once. You are one of them. That is enough. That was always going to be enough. So let me leave you where the whole story really points, which is not at a chalkboard, but at you. Remember the question that brought Bryce DeWitt around, the one that turned his disbelief inside out. Do you feel the earth moving? You do not. You are racing around the sun at 100,000 kilometers an hour, and you feel perfectly, completely still, and you have never once doubted the ground beneath you, and you were wrong the whole time, in the most ordinary way imaginable. Your stillness was never proof of stillness. It was only proof of what you were built to feel. And so the many worlds interpretation asks you, very quietly, to consider what else you might be failing to feel right now, not as a fear, as a kind of opening. The seamless single thread of your experience, the absolute certainty that there is one of you in one world moving along one line, might be exactly as trustworthy as the feeling that the earth stands still, real, vivid, total, and possibly, gently, an illusion of perspective. The version of you listening to this is one ripple in something far larger than itself, a single thread the others will never touch, and that thread is about to do what every thread eventually does. It is going to soften and slow and let the words blur and drift towards sleep. The others have already drifted. The one who turned this off an hour ago the one who never started, the one who is, in some far branch, hearing it for the first time tomorrow. They are all out there, if the equation is honest, each one certain that they are the only one, each one just as real as the you that is fading now. Only one thing is happening to you tonight, but everything else is happening too, somewhere quiet, somewhere you will never go, and there is something almost restful in that, if you let there be. You do not have to carry every road. You only have to walk this one, the single thread that is yours, all the way to wherever it gently leads. The others are taken care of. The others are already home.